Good day everyone. Thank you for attending this online presentation. My name is Buisan and I'm going to present our work, Efficient, Situated and Ontology-based Referring Expression Generation for Human-Robot Collaboration. This work is a joint work with Sarthou, Arthur Bit-Monnot, Clodic and Rachid Alami and was done in Toulouse, France at the LAAS-CNRS laboratory. During a collaborative task, the ability to refer to a precise object of the environment is crucial, and a robot must be able to do it. This problem is called the Referring Expression Generation Problem, or REG problem for short. The Referring Expression Generation Problem is defined by Reiter as being concerned with how we produce a description of an entity that enables the hearer to identify that entity in a given context. On the picture on the right, my robot partner can refer to the pen on the table only by saying the pen. If we add another pen, the robot needs to add an attribute to the description to avoid the ambiguity. It could say the red pen. In more complex cases, the description needs to include relations to other objects and their attributes. Here, the robot would say the pen in the green pencil box, adding the green attribute of the pencil box in order to refer to the pen. The problems presented before were pretty standard in REG works. However, in assertions scenarios, some additional issues must be taken into account. If the human does not know that another pen is under the box, the robot can only say the pen without any ambiguity. Moreover, the context of the task is important. If the robot asks me to give it the pen, it is implicit that it is referring to the pen that I can reach and not the other one. As we see in this comparative array, the REG problem has been studied for a long time and is still a domain of interest today. However, some important criteria for REG in assertions context were an open issue. The algorithm must be able to run on a multi-purpose knowledge base and not a specialized for this purpose. Then, type of objects must be considered as a minimal information. Finally, some attributes are easier for the hearer to understand than others. A REG algorithm must take this into account. To explain the internal representation and algorithm used in this work, we will use this simple example with 3 pens and 2 pencil boxes sitting on a table. First, our algorithm runs on an ontology. It is a collection of classes representing abstract types which can inherit from one another. Entities are then represented as an instantiation of these types. Only some types are labeled with the readable speakable name, pen, table, pencil box, meaning that only these types are verbalizable and thus can be used to generate the solution. Ontologies also contain a set of properties which can also inherit from one another and can also be labeled or not. These properties are then used to describe relations between entities or attributes of entities. In addition to the ontology, our REG algorithm needs other inputs. First, as the ontology may be used to store other pieces of information than the ones needed for the REG, some relations may be pointless in a referring expression. We thus provide our algorithm with a set of usable relations. Here, we state that a referring expression cannot contain weight or length attributes, for example. Because some relations are easier to understand than others, we represent it by setting custom properties. For example, here, the color property is easier for the hearer to understand than the hint properties, so its cost is lower. A robotic ontology can represent a large number of entities, and for example, represent all the pen in a building. Our algorithm thus needs to have a context. Here, the context is that we are talking about entities which are on the table T1. Finally, of course, we provide our algorithm with the entity we want to refer to. We will call it the goal entity. The aim of the algorithm is then to generate a set of relations and variables allowing the hearer to get the goal entity. Variable can be bound to any entity in the ontology. Here, the variable 0 can be matched to either P1, P2 or G1, given that it has the attribute color blue. However, some rules must be respected to generate a valid referring expression. To be directly used in the solution, an entity must have a label. Otherwise, the entity is represented by a variable that must be typed. Here, the variable 0 is not typed and thus could not be verbalized. Then, each variable in the referring expression must find a match in the ontology. Here, no green pen can be found. Finally, the variable representing the goal entity must have a unique match in the ontology. Here, both P1 and P2 can match the referring expression. Here is the final referring expression to designate P1, which can be verbalized as the blue pen which is in the blue pencil box. The algorithm we developed is based on a uniform cost search algorithm. It explores a graph where nodes are partial referring expression, starting with the given context, and edges are addition of relations present in the ontology. To ensure that each variable is typed, typing relations are added before anything else if a variable has no type in the partial referring expression. We compared our approach with two state-of-the-art algorithms each time on the dataset. Our approach gives the same results and is faster in all cases. Moreover, these approaches need dedicated knowledge bases, which can be hard to maintain in a complex robotic system. We also tried our approach on a large, realistically sized ontology representing a 3-room apartment with multiple furnitures and objects. For every entity, a referring expression has been formed in under 5 milliseconds, which is highly desirable in a human-robot scenario. Finally, our algorithm has been implemented in a robotic architecture and tested on a PR2 robot. We have shown that our algorithm is able to generate pertinent referring expression in real time on an evolving knowledge base, which is fed by a basic perception system. So in this work, we presented a definition for the reg problem applied to HRI, presented an efficient ontology-based algorithm, and evaluated it. In the future, we plan to use our algorithm at task planning level to get an estimate of communication cost in order to balance communication actions with other ones. Moreover, we want the robot to be able to learn the property cost during the interaction. I thank you for your attention, and if you have any question, my live version and my colleague Guillaume Sarthou's one will be glad to answer them.